Chapter 6: Static Routing. Routing is at the core of every data network. It is responsible for the transfer of packets from one network to the next. A router can learn about remote networks in one of two ways: manually and dynamically. Manually. Remote networks are manually entered into the route table by using static routes. Dynamically. Remote routes are automatically learned by using a dynamic routing protocol. There are some advantages of using static routing. For example, static routes are not advertised over the network, and this means it gives a better security. They also use less bandwidth than dynamic routing protocols, so there aren't CPU cycles to calculate and communicate routes. And the path used to send data is known. But of course, there are some disadvantages of using static routing. For example, the initial configuration and maintenance is time-consuming. The configuration is error-prone. There's an administrator intervention required to maintain changing route information. It doesn't scale well with growing networks, which leads to a cumbersome maintenance. It requires a complete knowledge of the whole network for proper implementation. Here are the differences between dynamic and static routing. In configuration complexity, the dynamic routing is generally independent of the network size, and the static routing increases with network size. For topology changes, the dynamic routing automatically adapts to topology changes, but in static routing, it is required an administrator intervention. In scaling, dynamic routing is suitable for simple and complex topologies, and the static routing is more suitable for simple topologies. In security, static routing is more secure than dynamic routing. For resource usage, static routing does not need extra resources, but dynamic routing does. For example, it uses CPU, memory, and link bandwidth. In predictability, the route in dynamic routing depends on the current topology, and the route in static routing is always the same. But static and dynamic routing are not mutually exclusive. In fact, most networks use a combination of both. So, when should we use static routes? We can use them when providing ease of routing table maintenance in smaller networks that are not expected to grow significantly. Also, when routing to and from stop networks, because a stop network is accessed by a single router, which is going to have only one neighbor. And when using a single default route to represent a path to any network that doesn't have a more specific match with another route in the routing table. This is an example of a stop network, where router 1 has only one way to reach others. This means that the address 172.16.30.24 is a stop network and router 1 is a stop router. Static routes can reduce the number of routes advertised by summarizing several contiguous networks as one static route. They can also create a backup route in case a primary route link fails. The types of static routes are standard, default, summary, and floating. Standard. The IPv6 and IPv4 support the configuration of static routes. In this example, is shown that router 2 can be configured with a static route to reach the stop network. Default. This route matches all packets. But how? So, a default route identifies the gateway IP address to which the router sends all IP packets that it doesn't have learned or static route. By configuring a default static route, a gateway of last resort is created. These routes are used when no other routes in the routing table match the packet's destination, and also when a router has only one other router to which it is connected. Summary. In order to reduce the number of routing table entries, we can have multiple static routes into one, only if the destination network's addresses are contiguous and the multiple static routes all use the same exit interface or the next hop IP address. Floating. It is used to provide a backup path to a primary static or dynamic route in the event of a link failure. But how? So, the route is configured with a higher administrative distance than the primary route, and if there are multiple paths to the destination, the router will choose the path with the lowest administrative distance. Static routes are configured using the commands shown in the screen, where the network address is the destination network address of the remote network to be added to the routing table. The subnet mask is the one of the remote network to be added to the routing table. This mask can be modified to summarize a group of networks. The IP address is commonly referred to as the next hop router's IP address. It is typically used when connecting to a broadcast media, for example, to the Ethernet, and it commonly creates a recursive lookup. The exit interface uses the outgoing interface to forward packets to the destination network. It is also referred to as a directly attached static route, and it is typically used when connecting in a point-to-point configuration. Configuration options. Next hop can be identified by an IP address, exit interface, or both. How the destination is specified creates one of these. Next hop route, when only the next hop IP address is specified. Directly connected static route. Only the router exit interface is specified. And fully specified static route, where the next hop IP address and exit interface are specified. In a next hop static route, only the next hop IP address is specified. And there is a term called resolvability, which is that before any packet is forwarded by a router, the routing table process must determine the exit interface to use to forward the packet. It takes two routing table lookup processes to forward any packet, and it is preferred to use a multi-point broadcast interface or a point-to-point interface. Configuring a directly connected static route with an exit interface allows the routing table to resolve the exit interface in a single search. Only a directly connected interface can have an administrative distance of 0. For point-to-point interfaces, you can use static routes that point to the exit interface or to the next hop address. And for multi-point broadcast interfaces, you can use static routes that point to a next hop address. In a fully specified static route, the output interface and the next hop IP address are specified. This is used when the output interface is a multi-access interface and it is necessary to explicitly identify the next hop. The difference between an Ethernet multi-access network and a point-to-point serial network is that this last one has only one other device on that network. And with Ethernet networks, there may be many different devices sharing the same multi-access network. To verify static routes are the next commands. show IP root, show IP root static, and show IP root network. The default static root is used when no other roots in the routing table match the destination IP address of the packet. Also, when connecting an edge router to a service-provided network or to a stop router. IPv4. The basic command syntax to configure the default static root in IPv4 is the next one showing your screen, where the IP root defines the static root. The first group match any network address, the second group match any subnet mask, and the last group is the next hop IP address or and an exit interface. To verify, the command show IP root displays the contents of the routing table, and show IP root static displays only static roots. In the symbols, we can have an S for static root and an asterisk for candidate default root. IPv6. The basic command syntax to configure the default static root in IPv6 is the next one showing your screen, where IPv6 root defines the static root. The next group matches any network address and prefix, and the last group is for the next hop IP address or and an exit interface. To verify, we can have the command show IPv6 root, which displays the contents of the routing table. And also we can have show IPv6 root static, which displays only static roots. And in symbols we can have an S for static root.
Now talk about classful network addressing. Released in 1981, RFCs 790 and 791 describe the initial allocation of IPv4 addresses in a classification system. This classification system focused primarily in network size, establishing the following classes. Class A addresses, which were intended for large organizations. Class B addresses, which were intended for medium to large organizations. Class C addresses, which were intended for small to medium organizations. The remaining addresses were reserved for specific uses. That's where we find Class D and Class E, as Class D was reserved for multicast addresses and Class E for experimentation and future use. Class A networks. The address range for this class goes from 0 to 127. It uses the first octet to identify the network portion of the address and comes with a total of 128 possible networks, where 2 of them are reserved for default routing and loopback testing, while the remaining ones are usable, each one capable of supporting over 16 million individual host addresses. The address range for this class goes from 128 to 191. It uses the first 2 octets to identify the network portion of the address and comes with a total of 16,384 possible networks, each one capable of supporting 65,534 individual host addresses. Class networks. The address range for this class goes from 192 to 223. It uses the first 3 octets to identify the network portion of the address and counts with over 2 million possible network addresses, each one capable of supporting 254 individual host addresses. Classful routing protocols. In classful routing protocols, the subnet mask is directly related to the network address. That is because it is determined by the first octet of the network address, and thus there is no need to include this information in updates. One example of this type of protocol is RAPV1. Inefficiency. One problem with classful addressing is its weights of address space. As we can see in the chart, Class A occupies 50% of all this space, but only 126 networks exist, and almost no one able to take full advantage of all the addresses that these networks offer. Where Class B suffers from the same issue, we find that Class C is very limited in its host address space, making this addressing scheme wasteful and inefficient. Domain routing. Documented in 1931, in RFC 1517, it replaces classful network assignments and enables the use of any prefix length bigger or equal to /8. Some of the benefits of this addressing scheme are that it enables route summarization, which implies that multiple routes can be summarized in a single route, and supernetting, which consists in assigning a route summarization mask smaller than the default classful mask. Route summarization. In order to perform route summarization, we have to perform the following steps. Step 1. List the networks in binary format. Step 2. Count the number of matching bits from left to right in order to identify the summarized subnet mask for the route. Step 3. Copy the matching bits and then add 0 bits to the rest of the address to determine the summarized network address. Here's an example of route summarization. We find that not only does it result as a consequence of classless addressing, as it benefits routing tables by making them have less entries in compacting multiple contiguous route addresses to one simple route. Classless routing protocols. Classless routing protocols advertise network addresses with their associated subnet mask. Some examples of this kind of routing protocol are RIPv2, OSPF, and ERGRP. Fixed length subnet masking. With fixed length subnet masking, the same number of addresses is allocated for each subnet, which most of the times results in a significant waste of unused host addresses because not all subnets have the same network requirements. Variable length subnet masking. Variable length subnet masking was designed in order to avoid FLSM address wasting by allowing a network space to be divided in unequal parts. This generally means that after subnetting a network, those subnets could be subnetted recursively in order to create various size subnets that could adequate better to network requirements. Instead, we can appreciate an example of VLSM, where we start with a network address of 10.0.0.0/8, and next we borrow 8 bits from the network address in order to subnet it into 256 subnets with a /16 prefix length. And finally, we borrow again 8 bits more from the network address in order to subnet the previous subnet and consequently have 256 subnets per subnet from the previous level, with a /24 prefix length. Implementing a summary route. Before implementing a summary route either on IPv4 or IPv6, 2 conditions must be fulfilled. One is that the network address to summarize are contiguous, and the other one is that all routes to summarize use the same exit interface or next sub IP address. IPv4. In this example, we first list the networks in binary format. Then, we count the number of matching bits from left to right in order to identify the summarized subnet mask for the route. In this case, we find 14 matching bits and pass them from a /14 prefix length to a decimal subnet mask. And finally, we copy the matching bits and then add zeros to the rest of the address to determine the summarized network address. In this case, we maintain the 14 matching bits that we found and fill the remaining bits with zeros. IPv6. In order to implement a summary route on IPv6, we must follow these steps. Step 1. List the network addresses and identify the part where the addresses differ. Step 2. Expand the IPv6 if it is abbreviated. Step 3. Convert the different section from hexadecimal to binary. Step 4. Count the number of matching bits from left to right in order to identify the prefix length of the summary route. Step 5. Copy the matching bits and then add 0 bits to determine the summarized network address. Step 6. Convert the binary section back to hexadecimal. Step 7. Append the summary root prefix obtained in step 4. In this example, we first list the network addresses and identify the part where the addresses differ. In this case, they differ in their fourth section. Then we expand the IPv6 where we found the different section. After that, we pass the different section from hexadecimal to binary. Next, we count the number of matching bits from left to right in order to identify the prefix length of the summary root, which in this case results in a /61 prefix length. Next, we copy the matching bits and add 0 bits to the remaining part of the address in order to determine the summarized network address. Next, we pass the binary section back to hexadecimal to finally append the summary root prefix length obtained in step 4. Implementing a floating static root. In order to implement a floating static root, we use the same command that we have been using along this presentation, which is iproot. But in this case, we add to the tail of the command the administrative distance that the static root will have, which if not present defaults to 1. True. Networks are vulnerable to forces that can change their working status and can affect the performance of a static root. Some of them are interface fails, connection drops by service provider, links oversaturation, and wrong configuration entered from an administrator. But in order to address these issues, we can use the common troubleshooting commands in iOS, which are ping, traceroute, show iproot, show IP interface brief, and show CDP neighbors detail.